Okay, good afternoon, everyone. We're very happy today to have Carmen Rovi from Loyola University in Chicago, who is going to tell us about cut and paste invariants and invertible TQFTs. Carmen, please.
Okay, so thank you very much. Thank you very much, Hisham, for the introduction, and thank you for having me at the seminar. So yeah, so cut and paste invariants and invertible TQFTs. So this work was joined with a student of mine, Matthew Schembauer, and it was originally based on a project that Greg, Teichner, and Stolz were working on. So it was based on their original idea, and then we added a couple more results in our paper. So okay, so let me get started with an introduction. So first of all, let me give you a little bit of a warm-up of what the notion of cut and paste means, or what the classical scissors congruences means. Because in this talk, we're going to be focusing on manifolds, but the notion of cutting and pasting is actually a much more general idea that occurs also in geometry, and it can be from very, very complicated notions to actually very, very classical, going back even to the Greeks. So this is what I have on this slide is really a very, very classical problem. Here you on the first picture you have cut and paste operation. So how does this work? Well, first of all, we're starting with a certain polygon, and then we decide to cut it in a certain way. So we cut it into different sub-polygons. And once we do the cutting, well, then you are going to rearrange those pieces and put them back together. Of course, there are certain rules on how you're going to put things back together. For example, you see that you're not taking maybe one of the pieces and putting it on top of another piece. They're always glued via their boundaries. So so you rearrange your pieces. You not delete them. You just rearrange them. You rearrange your pieces, and then you get a new polygon. So what we see here is that this first polygon, the original first polygon, and the result after this operation of cutting and pasting, you could say that these two polygons are cut and paste equivalents, or scissors congruent. A little bit more formally, you could say, well, you have your polygon P, you divide it into the union of subpolygons P sub I, and then you do the same thing with your polygon Q, which is also subdivided into pieces. And you could say that these two polygons are scissors congruent if the pieces coincide, just as we can see from this picture. This would be the PIs, and of course, now if you look at the other polygon, you just relabeling them to call them QIs. But if you want things to be scissors congruent, they should coincide. Okay. So this is what it is, and so this is the main idea. Now, next question is, well, what happens? How do we generalize this problem? So, you could think about going up in dimensions. So you could think about, we thought about polygons and we saw how it worked, but now how about three-dimensional objects? So would you say that for polygons, it's pretty obvious that the only invariant is the area, but is it true in the when you go up in dimensions, when you go in dimension 3, is the volume the only cut and paste invariant? And the answer is no. That's a little bit of a surprise, but that was an important problem by Hilbert, and Hilbert gave this problem to a very good student who was then. And he thought, well, this is a very hard problem. It's going to take him a long time. So maybe like about a year later, Dan had already figured out that for example, this tetrahedron and this little cube, even though they have the same volume, you do not have a cut and paste operation that can convert one into the other. So they're not cut and paste equivalent. And not only that, he actually constructed an invariant, which is called the Dan invariant. It's just a formula depending on the angles and internal angles, but that invariant actually detects that the tetrahedron and the cube, even though they have the same volume, they are not cut and paste invariant. They are very interested invariants as you go up in dimension. Okay, that's 3-dimensional. Let's push our dimension up one more. So in 4 dimensions. Okay, so in 4 dimensions, we have maybe like a generalization of the notion of volume and also some generalized then invariants adapted to, obviously, to the correct dimension. But it was proved, actually, and it's not recent, but compared to the work of Den, this from the 20s, now we have like this result in 4 dimensions quite a long time later, it's 1972. But it was proven by Jensen that this 4 volume and the Den invariant are the only cut and paste invariants there. Okay, 1 more dimension up and we get to 5 dimensions. And now it's a big mystery and it's a very difficult problem to tackle. It's actually an open problem. What invariants do you have? What cut and paste invariants do you have? What are the requirements there? How do you know that something in higher dimensions is going to be cut and paste equivalent to something else? So the problem gets more and more difficult, especially in geometry. It gets more and more difficult as we go up in dimensions. Now, this is more geometric, but I want to focus on manifolds in this talk. So let me draw the analog of what the cut and paste operation that we've seen in polygons and polyhedra. How does it look like when I go into manifolds? And this cut and paste operation, well, it was because it existed before this work, but this formal way of formalizing this cut and paste operation was actually first explicitly written out by a group of authors, Karras, Craig, Neumann, and Ossa. Okay, so how does it look like? So the picture on the right-hand side is already very telling. Let's go step by step. So we start here with a smooth, closed manifold of, say, dimension n, and we are going to choose a co-dimension 1 smooth submanifold with trivial normal bundle. So in here, it's already highlighted a little bit, but the co-dimension 1 submanifold that we're choosing has actually a trivial normal bundle here. So that's important. So because when we do the cut operation, we actually want to have a nice little color around one boundary and a nice little color around the other boundaries. So that's what that condition of the trivial normal bundle there is for. Okay, so if you're playing by the rules and doing your cut along this framed co-dimension 1 submanifold, then you end up with these 2 pieces, M1 and M2. And obviously the boundary of these 2 manifolds, because it was the place where it was where you've cut, those 2 boundaries, this boundary and this boundary component, they are the same manifold, at least the very least they are diffeomorphic. So that means that if they are diffeomorphic, I can choose some diffeomorphism and then glue things back together, paste the 2 components, paste them back together via some diffeomorphism. If I chose the identity, well, I would go back to the original manifold. But if I choose something else, well, then I'm getting to a new manifold. And in a second, we're going to see a slightly more explicit example than this sketch here. Okay, so you've done your operation, and then just as we did with the polyhedra and the polygons, we would call our original manifold M. We call it cut and paste equivalent to this new manifold that we have constructed by, say, taking M1 and gluing M1 to M2 via this phi, where this phi is the gluing diffeomorphism. Okay, so this is the cut and paste operation. Let's move on.
Can I just ask a trivial question?
Yes, sure.
Do we want to generalize this manifold with boundaries and corners so that the scissor congruence is a special case, or do we not want to do that?
Okay, so that's a really good question. let's see. So we're not going to see manifold with corners in this talk, but you know, like with some collaborators, I was working on trying to give some K-theoretic notion of these manifolds, and then we did bump into that problem because let's see, so because essentially because when you cut a polygon, you get little subpolygons, and they are objects of, let's say, of the same nature as the original polygon. You know, it's a polygon, it has its boundary. This is a little polygon, also has its boundary. Manifold world is slightly different because you start with an object here, which is of the nature of that object is a closed manifold. And when you cut, you get manifolds with boundary. Now, with polygons, again, back to this slide, I could have said, well, I'm going to now do more cuts on this thing. I still have little subpolygons, nothing happens. But if I go ahead and try to cut one of these manifolds, how am I going to cut it? Well, one possible way to cut it would be like this, right? And you could do like that. And then you are getting manifolds with corners. So, you know, that's a good question. It's actually one direction that you could go to analyze, like, further cutting and pasting, or there's different routes you can take. Maybe I don't want to like diverge totally in that direction, but it is a really good point. And manifolds with corners do occur in our work that we've done with the K-theory, you know, trying to capture this as a K-theory spectrum. So it does.
I see. Thanks.
Yep. Okay, good. So this is the notion of cutting and pasting on manifolds. Now let's formalize this a little bit more, because well, this operation gives rise to a certain, just as you have cobordism groups, you also have these cut and paste groups, which are defined a little differently. So let's see how they are defined. Okay, so we start with this monoid of diffeomorphism classes of smooth, closed, oriented, n-dimensional manifolds. The operation is disjoint union. And then what we're going to do is, well, we're going to take the Grothendieck group of that, and we're going to quotient via a certain relation. Okay, so what is this relation? That relation is what's going to give us the cut and paste flavor for our group. And that relation is actually telling me what goes into the same class. And what we are identifying is we are identifying manifolds. So this is a manifold. It's made out of two pieces, include via some boundary via this phi diffeomorphism, but it is actually equivalent to this other manifold, which is just like with the example with the polygons. It's made out of the same pieces, M1 and M2, but the gluing is done differently. So that's exactly the things that you identify in the cut and paste group. Things that are made out of the same pieces, you glue via different diffeomorphisms, and those get identified to be the same because they are cut and paste equivalent. And a little bit of notation here, well, I was already saying, but this phi and the psi, well, they are, like as we saw in the previous slide, they are diffeomorphisms of the boundaries that occur when you've done the cutting. And again, if you're taking care of orientations, well, maybe you want to say that this symbol here just means that the other manifold has the opposite orientation. So, you know, you do get like orientation preserving diffeomorphisms when you are gluing your boundaries. Right, so that's the definition of the SK group. The SK stands for schneiden und kleben. Actually, that's just cutting and pasting. So this is the definition. Let's see what we can do with this group now. Okay, so as promised, I'm going to give an example of an actual cut and paste operation on manifolds that's not just schematic, it's actually a real thing. So suppose that we start with this torus. It could be a 2 torus. And we do our cutting. We're going to cut along 4 places. So we're going to choose this submanifold, which is in various pieces. And so we do our cutting, and now we get these four pieces here. So now I'm going to rearrange my pieces in this fashion, and then I'm going to do the gluing. Also already indicated a little bit down there. So I do the gluing or the pasting, and I get 2 tori. So this is now interesting because put into like a formal language, what you're seeing from the picture is that your 2 torus from the beginning actually equals, or is the same in the SK group, is the same as the disjoint union of 2 tori. So actually twice the class of the torus. And well, if something is going to have to be equal to twice itself, then that something has to be 0. There's no other way around that. So this is interesting, because then this tells us that in cut and paste groups, tori are going to represent the 0 class. And this is just an example. It's indicating dimension 2, but this is actually true for any high dimensional torus, or even for mapping tori. So you could have had some mapping torus, any mapping torus, is going to be the class of any mapping torus of any dimension is going to be 0 in whatever dimension you've chosen. And that is an important ingredient in the whole story here of cutting and pasting. Okay, so this is the construction of the manifolds. That's the group. Now let's try to understand what are invariants under this cut and paste operation. So cut and paste operations and cut and paste invariants actually do not notice the cut and paste operation. So what do I mean by that? So what I mean is that if you're taking 2 manifolds here, this n and n prime glued via either phi or psi, these two things are cut and paste equivalent. And now I'm taking my lambda here, which is some manifold invariant, and I'm computing that manifold invariant on this first manifold. I'm also computing it on the other manifold, and it turns out I get the same result. So that's what you call an SK invariant, a cut and paste invariant. So what are examples of those invariants? So the 2 main cut and paste invariants, SK invariants, are the Euler characteristic, because, well, you know, you have the gluing formula for the Euler characteristic apparently has 1 extra term. So you could have like the Euler characteristic of one piece plus the Euler characteristic of the other piece minus the Euler characteristic of the intersection. But we're talking about manifolds, so that's going to that intersection is just going to disappear because of dimension reasons and concurrent duality. Okay, the other invariant, the signature invariant, this is the reason for this to work here is Novikov additivity. So, you know, Novikov additivity is already telling you that it doesn't matter how you glue your manifold, the signature, if you've actually glued along the whole of the boundary and you don't have any dimension 2 error of any type, you've done your gluing as you should, then Novikov additivity tells you that it doesn't matter how you glue. So that is actually the other very, very important cut and paste invariant. So these are actually just the 2 SK invariants, and all other SK invariants are just linear combinations of these. So in that sense, SK invariants do not get literally that complicated. There is another generalization of this notion of cutting and pasting, which gives rise to a much bigger family of invariants. And these are called SKK invariants. So SK stands again for schneiden und kleben, cutting and pasting. And SKK invariants stand for schneiden und kleben, kontrolliert. So the second case for kontrolliert is there's a way to control this error term. So what's the difference between one and the other? So you see here, it has to be perfect. The 2 invariants have to give you the exact same thing. So they, you know, you subtract, you get 0. With SKK invariants, you're a little bit more loose. So you apply your invariant to these two cut and paste equivalent manifolds, and you get some error term. And why is it controlled? Well, it's actually controlled just by the diffeomorphisms, by the phi and the psi that you've glued along. So you could actually express this error term. So you take your invariant, and it's only depending on phi and psi. And by actually relaxing the definition in this way, you're actually getting a lot more invariance. Well, first of all, you do get the Euler characteristic and the signature because, well, that error term could have been 0. So why not? And then you would be back in the SK situation. But you don't only get those invariants, you get a lot more things. So one important thing is that you do get all Bordism invariants are SKK invariants. And in addition to that, you also get this interesting invariant. I mean, the formula is just maybe like looks a little small there. Let me zoom. So the semi-characteristic. The semi-characteristic is an interesting invariant. It's the Euler semi-characteristic, Euler semi-characteristic, and it works. What's the formula? So a little bit similar to the Euler characteristic. You're taking 4K plus one-dimensional manifold, and what you're doing is you're adding your Betty numbers up to the middle dimension, so up to 2K, and you're taking that sum modulo 2. So that's how you compute Euler Kerber semi-characteristic. Okay, so those are the invariants. We also have an SKK group. So an SKK group, so the definition is, again, you have your monoid of all of these diffeomorphism classes of manifolds, take your Grothendieck group, and now you're modding out via a slightly more complicated relation. It is in the same flavor as the SK relation, but it's a little longer to express. So here it is on this line. So let's see what we are looking at here. So we have, first of all, we have here M1 and M2 glued via phi. And on the other side, we also have M1 and M2 glued via psi. So those two red boxes right now, those two things are actually cut and paste equivalent. But we also need this other information from the other manifold. So we have now another manifold, which is glued via psi, via two different pieces, and then it's cut and paste equivalent to this. Those are the two cut and paste equivalent manifolds. But there's also a relationship here on what the diffeomorphisms are. So we see, we should pay attention on where the phi and the phi is occurring. So phi and psi, and then also for the other manifold, phi and psi. If we want to see a little picture of how this works, so we are getting our 4 pieces, M1, M2, M3, and M4. And what I'm doing actually is I'm keeping everybody staying put. They're all staying in the same place. And what I'm doing is I'm taking the two diffeomorphisms and swapping them. Clearly, you have, in order to be able to do this, you need the 4 boundary components that appear in this picture have to be all diffeomorphic. Otherwise, you wouldn't be able to do this mix and match of manifolds and diffeomorphisms. So this is what the relation in your group. And you take that relation, and that's how you define this SKK group. And that SKK group actually has a pretty interesting relationship to cobordism. So this is work from maybe the 70s. This one, written by this group of 4 authors, Karras, Craig, Neumann, and Osser. So they worked on trying to understand the connection between cobordism and cut and paste groups. And we've seen 2 different cut and paste groups. This SKK1, which is the slightly more powerful, in a sense, the bigger group. We've also seen SK group, the one we saw at the beginning. SK and Bordism, like oil and water, they do not match. They just, there's no map from one to the other. But SKK actually does subject onto cobordism. As we saw over here, Bordism invariants are SKK invariants. So that already gives us a kind of like a motivation for this exact sequence. So what things in SKK are going to go to 0 in Bordism? Well, that's this kernel over here that's computed. And that is can be interpreted as something generated by spheres. You could also think of it but it also arises from homotopy theory. There's many explanations on why this kernel is what it is. But key thing here is that we do have a computation, and let's see. So what interesting things can we see here? Yeah, so they are all detected by SKK invariants. One interesting computation here is this C2 right here. So that C2 right there in dimension 4K plus 1 is detected by the semi-characteristic. So you know, it's pretty interesting where each of the invariant actually detects. Let's see an example of this exact sequence in action. So let's suppose that we take I'm taking the exact sequence from before, and I want to look at how it looks like for n equals 5. So we're going to look here in the 5-dimensional situation. So first thing is I'm going to reveal here that the spoilers that the SKK in 5 dimension is Z2 plus Z2. So what are the well, it's C2 plus C2. So what generates each C2? So geometrically, you could be thinking of these two generators. One of them is going to be, well, they're both a little similar. If you look at the picture, they both look a little similar. So what are we looking at here? So we are looking at two mapping tori. The one here on the left is, well, they're both mapping tori of CP2. So CP2 is a 4-dimensional manifold. So I'm taking that CP2 and I'm taking CP2 cross an interval. Okay, this is an interval. So CP2 cross an interval. Also on the right-hand side, CP2 cross an interval. Now the difference between these two mapping tori comes from how I am gluing these to different ends. So on this side, on the left-hand side, I am going to be gluing via the identity. So if I glue via the identity, then the resulting mapping torus, or the resulting manifold, is just a Cartesian product of S1 and CP2. On the right-hand side, though, I'm doing something a little different. On the right-hand side, I'm taking the complex conjugation map. So from CP2 to CP2, this is complex conjugation. And I'm gluing via this like slightly more elaborate, more difficult diffeomorphism. It turns out that this manifold that arises here is one possible representative. It's cobordant to the representative of the class that makes this group non-trivial. So if we are looking at there, then well, what I'm seeing here is that this speaking, like loosely speaking, this C2 here gets sent to a different copy of C2 on this side, the same copy of C2, because this manifold that generates that C2 actually is also generating something in cobordism 5, and that is actually non-trivial. It's actually detected by Stiefel-Whitney numbers. So yeah, so this manifold actually gets sent to 1 in your C2, or to the class of the Wu manifold, and to the class of this in cobordism 5. Okay, so that's one copy of C2. Now, where does the other copy of C2 come from? Well, if I actually looked at this manifold on this side, so the S1 cross CP2, and I try to find, well, what is that in cobordism? If I try to push it over here, I'm going to get 0, because you know this is actually something that bounds. But if I compute the semi-characteristic of this, and that's not difficult, that's just by using the Keener's formula and looking at your Betty numbers, you just do a little bit of a computation, you actually see that the Kervaire semi-characteristic of this manifold is actually non-trivial. So you can actually see how this manifold, this other C2, which would be trivial in cobordism, is actually non-trivial in SKK, because it's detected by the semi-characteristic, and that's actually something that belongs into the kernel because we have an exact sequence. Okay, so that's an example of how the short exact sequence works in dimension 5. Okay, so let's actually see a little bit more about SKK. I want to mention, we're not going to go into depth into this, but I wanted to mention that this SKK group has different interpretations. So the interpretation that I'm working with is this cut and paste definition of the group, but it can also be interpreted as vector field Bordism. So those just coincide with right-hand vector field Bordism groups. And they also have some very interesting, like more homotopy theoretic interpretation as pi naught of this Madsen-Tillman spectrum. Maybe it's also not something I'm going to go into this talk, but just I thought it's a very interesting connection, and I thought it was interesting to mention that. Also a little bit because now we're going to be moving on into the connection of this group and invertible TQFTs. And it turns out that this has been investigated from different sides. So there is work connecting the notion of invertible TQFTs and this more homotopy theoretic notion of the SKK groups, and maybe even beyond that. So there's a very interesting paper by Grisham Priest investigating that connection right there. And of course, then we also want to make the connection with our more geometric notion of the cut and paste group. And as I mentioned before, well, the work in this direction, making the connection with the geometry, well, that was Craig, Teisner, and Stoltz. And then, well, the original seminal work, and then the paper that a paper that I myself wrote with Schembauer. Okay, so this is the route that we're going to take now, where I'm going to talk a little bit more about this connection of invertible TQFTs and this cut and paste version of SKK. Right. So before we jump into seeing the connection, and I think that your seminar has real experts in this, but just for the sake of anybody who is maybe not an expert or work on something else, let me review a little bit what topological quantum field theories are. Okay, so definition. So an n-dimensional TQFT, the n here is important. It's going to give you the dimension of your TQFT. It's a functor. It's a symmetric monoidal functor because it does work well with disjoint unions and tensor products. So it's a functor that is going to be a functor between two categories. It's going to be a functor between the cobordism category and a category of vector spaces. And what does the functor do? So the functor a little bit works like a translator from geometry. If we're looking down here in the picture, it's translating the geometry into some algebra. So how is it doing that? So to each n-1 dimensional manifold, now I want to point again to the dimensions here, an n-dimensional TQFT, that n refers to the dimension of the cobordism right here. So that n is this n is this n. And then, of course, if you're taking your cobordism to the n-dimensional, your boundaries are one dimension less. So these sigma manifolds they have here as boundaries are n-1 dimensional manifolds. What does the functor do to those? So those manifolds are going to get assigned a finite dimensional vector space, which I denote here by, well, the functor applied on the manifold. And likewise, so this is a vector space, and this is also a vector space. On each end of that map, we have vector spaces. What does my functor do to each Bordism? Well, the Bordism is sent to a linear map. So we get vector space, and then the cobordism gets sent to a linear map. So this thing here is a linear map. Right. So already, Adia already gave a very interesting, very important paper on how to axiomatize these TQFTs. So I'm going to need some of those axioms. So I'm going to go through some of those axioms, and there's more axioms than what I'm going to talk about here. We're just going to go through the essentials that we're going to need later. But you know, there's quite a lot of axioms. It's of course in our paper, it is done a little bit more in detail, but just for the sake of time, I'm going to just do the talk about the axioms that we really need. So first axiom that we see here is about gluing. So suppose that you start with a cobordism, you have another cobordism, and you can glue those two cobordisms via this boundary. What does a TQFT do to that? How does that translate into algebra? Well, just as before, each of these boundaries, each of these sigmas, is getting sent to a vector space. So vector space, sigma 1 also gets a vector space, sigma 2 also gets a vector space, and then you have these two linear maps corresponding to the two cobordisms. The importance of this is that it behaves well. So what do I mean by that? Well, I mean by that the taking the functor on the whole of the composed cobordism is actually the same. It will give you the same map as first taking the first linear map and then composing with the next linear map. So essentially, the axiom can be summarized into this line here, which tells you, well, the functor behaves well with respect to composition. So that's one important axiom. Another axiom that we're actually going to need is what happens if I evaluate my TQFT on a closed manifold, and how I may even understand in a closed manifold in this context. Well, okay, so a closed manifold can actually be understood as a cobordism as well, because I could be thinking, well, you know, if you look up here in this picture, you do have like a boundary component, another boundary component, and you have your n-dimensional manifold there in the middle. Well, now you have your n-dimensional manifold here in the middle, but the boundary component just happens to be the empty set. And the empty set is like this chameleon, where they are allowed to have the dimension of whatever you need. So this empty set right here would actually have n-1. It would be n-1 dimensional, because it just takes the color or the dimension of what's surrounding it. So if you need it to be n-1 dimensional, that's what it is. So yes, you can understand closed manifold as a cobordism between these two empty sets. What does the TQFT do to that? So the empty manifold gets sent to the ground ring, my little k here. Of course, on the other side, the empty manifold gets sent again to the ground ring. And then there's something very interesting happens, because your cobordism, your manifold here, gets sent to a linear map, but it's a linear map between two copies of the same ground ring. So essentially what you're doing there, you can identify that with a scalar. And what you can see there is that now you are taking a closed manifold, and by doing this operation, you're getting a scalar. Well, that's exactly what manifold invariants do. You evaluate your manifold, and you get some scalar or some algebraic information out of it. So what you're achieving here, what your TQFT here is doing, is actually giving you a manifold invariant. That's an important notion. Okay, we can also talk about the category of TQFTs. So the category of TQFTs, I'm going to call it of n-dimensional TQFTs. Just to recall that we're talking about n dimensions, I'm going to put it here in the notation. And also to remember what's our ground ring, that's also there in the notation. So what are the objects in this category? So the objects are going to be n-dimensional TQFTs. So in the previous slides, we've been seeing what one TQFT looks like. So now we have you can define different TQFTs, and those are going to be the objects in this category of TQFTs. right? So what are now the morphisms in that category? Well, they're going to be natural transformations of TQFTs. If you have a functor, you have another functor, what you need is a natural transformation. And okay, maybe we are going to want in the next few slides, we're also going to want some notion of invertible objects in this category of TQFTs. What do we mean by that? Well, if I give you a certain TQFT, can I find an inverse? So can I find another functor such that, you know, when I'm taking this tensor product operation, I get the identity TQFT. So you do have a notion of inverse in this context. And that's, as I said, this is important for us in our work because we want to work with invertible TQFTs. We do want this notion of TQFTs that actually have an inverse in the sense that I just mentioned. Right, so here's a definition of what an invertible TQFT is. What do we need? So one thing we need is that the vector spaces, you have your closed manifolds, so your boundaries, and you're assigning something to that you're assigning a vector space. The functor assigns a vector space. You need that vector space to be one-dimensional. Otherwise, when you take tensor products, things are going to spiral out of control. You know, if you allow your vector space to be, say, two-dimensional, and then you're taking tensor product, you're going to have something four-dimensional. You don't want that. You want to keep your vector spaces one-dimensional. So this is necessary for invertible TQFTs. And another important necessary aspect of the invertible TQFTs is that, well, every linear map is actually invertible. That's the whole point. Okay, so the set of all TQFTs, of all invertible TQFTs, actually forms a group under the tensor product operation. We do have our inverses, we do have closure because of this one-dimensional restriction. So we could go through all of the group actions. This set actually forms a group. And that's actually very useful for us because now I'm going to be relating groups via a certain short exact sequence. So this is now part of my work with Schoenbauer. And here in this short exact sequence, we see in the middle, this middle group here is the group of, okay, so let me actually write it down. So this is a group of n-dimensional, that's what this little n here stands for. So n-dimensional invertible TQFTs. Just to make things a little bit more concrete, my ground ring is now going to be the positive reals, so TQFTs. And okay, so that's a group. If we look at other groups in this exact sequence, the other interesting groups is to the right. So here we are now seeing SKK again. Remember this, our cut and paste group. What am I taking here? Well, I'm taking classes in SKK and I'm taking homes to the reals. I'm working multiplicatively now. I'm taking the reals, but essentially what I'm taking here is just SKK invariants. So all of those homes are going to be SKK invariants. So they are real valued SKK invariants. So now this is already taking shape because now we are seeing how the well, there's a group of TQFTs and there's a group of real valued SKK invariants. The kernel is just maybe not even worth like well, I mean, it's worth mentioning, but it's not a really very complicated kernel. It is just any TQFT that will evaluate to a trivial SKK invariant. So anything that's, you know, it's what you could expect for the kernel. SKK invariants that actually are one in this case because we are working multiplicatively. So anything that gets to be trivial when you get over here, then that's in your kernel. Okay, so this is the exact sequence. This is actually that's the punchline. But let me give you a little bit of like a motivation of why does this exact sequence even make sense. So let me give you a little bit of the idea of the proof of why that exact sequence makes sense. So we are going to be thinking about two manifolds here. And so if we observe here, these two manifolds are both made out of two pieces, M1 and M2, and M1 and M2. And then I've done some gluing. This is a slightly thickened gluing so that we have something to work on, like in the middle. But this is just a mapping cone of my chosen diffeomorphism on this side, which is the phi. So essentially, this is just M1 and M2 glued to each other via phi with the gluing a little bit thickened. On the other side, well, very similar manifold. Now I'm gluing via a different diffeomorphism type C. So the thing in the middle is a different mapping cone. Well, there are two manifolds. We've already seen how a TQFT can be evaluated on this closed manifold. So I'm going to do that. So suppose I call my TQFT tau, and I'm seeing, well, this piece, okay, you're thinking of this now as this linear map. And this linear map is the composite of three things. It's the composite of M1, I'm not going to draw there. So it's the composite of M1, the composite of this mapping cone, and then the composite of the third piece. So we are taking the TQFT of the composite. Okay, that's for the first manifold. Suppose that now I take the other manifold and do the same thing. I'm also going to have the TQFT, same TQFT evaluated on the other thing. I'm going to take those two. Well, they are actually scalars because the TQFT sends this to the ground ring. So this is getting sent to, in this case, R and R. So this evaluation of the TQFT on the glued cobordism is a linear map, but you can identify that with a scalar. And that's what I mean by dividing these two scalars. So you're going to get two different scalars from two different results from the two manifolds. I'm going to divide them. Good. So if I can divide them, then I'm going to use the first axiom that we saw, that the functor behaves well under composition. So I could re-express both the denominator and the numerator and denominator as the product of these three scalars that I get out of my three linear maps. So I can decompose my expression in this way. And of course, these are just scalars. I can just cross things out, and yeah, I have the result. Okay, so what does this result tell us? Well, what this result tells us, after, if you observe carefully what's happening there, what does that depend on? So actually, that term only depends on, we only playing there with the only remaining information is the mapping cone. The only remaining information is your phi and your psi. So the only remaining information are the diffeomorphisms that you started with. And if we remember how we defined the SKK invariance only depends on the gluing diffeomorphisms, just as exactly what's happening with this TQFT thing. So remember that if I take an SKK invariant and evaluate it on this manifold, and I also evaluate the same SKK invariant on that manifold, I get this error term, which only depends on phi and psi. And this is exactly what's happening when you're evaluating that TQFT. So that kind of like gives you an idea of why there should be this connection and why there should be this exact sequence relating invertible TQFTs and the SKK invariants. Okay, so just to give a little bit more content here. So we have our exact sequence. One interesting thing that we were able to say about this exact sequence is that it actually splits. So we have this sequence splits. I wanted also to motivate a little bit why the sequence splits. The proof is actually rather long. It takes a few pages in our paper. but just very quickly, I want to give you a little bit of a flavor of how that is constructed. Okay, so we know from our original, maybe let me recall that we had a short exact sequence that involves SKK and cobordism. We actually saw an example of this before. So we had this short exact sequence, and we know what that kernel is. We could also know what that kernel is with real coefficients. So I also know that this short exact sequence, the one that's in the bubble right now, so this short exact sequence also splits. So this SKK group can be expressed as cobordism, and that group that's generated by spheres. I know the computation. So by using that notion, I can now translate this into, well, I'm looking into the reals and I'm looking at a computation. So I'm actually seeing that this can be expressed as, well, for every n odd, it's just going to be 0. Then we have this form for k plus 2 dimensions. This is that is a subgroup generated by the Euler characteristic. And in 4 dimensions, we have something a little bit more complicated. We have this subgroup generated by Euler characteristics that doesn't complicate the story at all. But we also have this, which arises from this component of cobordism. So, you know, cobordism invariance right there for 4 dimensions. And the proof of the splitting of the exact sequence is not complicated at all on these components, but it does require a little bit of work if you want to see, like, how does this splitting work when I'm restricting my homes to this specific component in 4K dimensions. Now that's a question. You know, you have your component in here. You want to see how that splitting works. So that's what I want to explain in the last few minutes. How does that splitting work on the difficult term? Actually, that's the other ones are not almost trivial. Okay, so yeah, so here's the question again. How does that splitting work? So, well, first of all, let's take some cobordism invariant here. Now we're specifically talking about 4K dimensions. So given this, what I want to construct a TQFT, because I'm in this home here. I want to go back and I want to construct a TQFT out of that. Okay, so given that, I want to construct the TQFT. Let's see what we can do with that. So one fact that is very helpful here is that the 4K minus 1 dimensional cobordism group is always finite. Suppose that for the particular dimension that you choose there, it's finite. Well, it's always finite, but suppose that you know that it's finite, and you say, well, it has order L. You're choosing that order right there. Okay, so since it's finite, since this group is finite, that means that if I take, in the worst case scenario, a generator, I take something with a manifold in here, which is 4K minus 1 dimensional, and it's close connected, and suppose it could be a generator, it could also have been a boundary. In that case, it's no problem. Or it could be that it's not a generator, but what I'm going to say actually works, is that if you take such a manifold and you know that your group has order L, well, then you know that if you take L copies of this manifold, suppose L is 2 in this picture, if you take L copies of that manifold, then you are going to be able to find some Bodism here that actually makes that disjoint union of copies of your sigma here into a boundary, because it's finite, because the group is finite. So if you think about, suppose that this was a generator and the group is finite, is of order 2, then you take 2 copies of that sigma and you're going to see that bounds. So once you realize that, then you can think about, well, I'm going to construct, the aim is to construct a 4K dimensional closed manifold, but there's a trick of doing that. So the way I'm going to do this, I'm going to take any cobordism. And now these boundaries are allowed to be whatever you want. And this is a 4K dimensional cobordism. And I'm going to construct a closed 4K dimensional manifold by doing the following. And now comes a big picture. We'll look at it step by step. So I'm going to take that W manifold, and I'm going to take L copies of it. So L being the order of your group here. You're going to take L copies of that, and now I'm going to close off these boundaries by saying, well, can I take my 2 copies of my sigma 2? Can I find something that like makes that a boundary? Yes. Can I do it with some manifold? Yes. You can do it every single time. So you do a repeat. You do all of that, and you are able to construct this closed manifold. Okay, now you have this closed manifold, and what do you do with it? Well, this closed manifold is going to be something which is possibly non-trivial in your 4K dimensional cobordism. Now, we were trying to, we had this invariant, and we compute that invariant on this closed manifold, and it gives me this sigma of the closed manifold, whatever that gives. Good. So that with this allows us to define a homomorphism by saying, well, you had your invariant in here in cobordism, but it also lives in there. You look at what that invariant looks like under this, and then you're evaluating that on this W manifold. On that W manifold, yes, no, yes. Well, yes, but you've double counted a lot, because here you've counted like L copies of your W. So since this is multiplicative, you are now having like that too many times. So that's why you have this 1/L up here. You have to get back to just trying to get just one the correct number actually. So that's the once you define the homomorphism, you still have to do a little bit of work. You have to check that this homomorphism satisfies the TQFT axioms, which it does. And there's also a little bit of a check to see that actually defines a splitting, but that's actually done in detail in the paper, and it does work. So we got our splitting. And if you do want to see more details, the paper is by now published. It's on the archive, and I think I'll just stop there. So thank you so much for your attention.
Thank you very much, Carmen. Questions for Carmen? Okay, so I have a question. So earlier you said you're gonna follow a geometric approach. Is what made it geometric the fact that it's R valued? Is that the idea?
Just let's see. So what I meant by the geometric approach was more like because these SKK groups have so many different interpretations. So you could go like vector fields, or you could go via the homotopy theoretic phi naught of this spectrum. That's by geometric I meant that well, the cut and paste version of the group actually.
I see. Okay, yeah, that's very interesting. So when you looked at that 5-dimensional example, right? So you had 2 generators. One of them is S1 cross CP2. And earlier you had said that the kernel IN in general is generated by spheres.
Oh yes, I see.
Like
okay, so it's generated by spheres. It doesn't mean that okay. Oh yeah, I see what you mean. Oh, this is going to be difficult. How do you see the sphere in there? The fifth sphere.
S1 cross CP2 is very close to a sphere. S1 bundle over CP2 is a sphere.
Yeah.
That's is it like that?
I think so. That's a pretty cool geometric argument. You could just cheat and evaluate the invariant and see that they give you the same class. But that's a very cool way to see it. Oh, nice. I hadn't thought about that, but it's pretty cool. Yes.
Okay, good. All right, excellent. Any other questions for Carmen? I was actually curious in the beginning when you got two tori from one torus, how does it work in higher genus? I guess one can look at it as an exercise, but is this
Okay, yes. Okay, so higher genus. Okay, maybe let's try to draw some little pictures here. So
I'm just wondering whether it's known, done. I mean, you don't have to do
yeah,
it.
absolutely. So I'm just trying to think about one cut and paste operation. I know that the two torus is actually okay. Now I'm blanking on what it actually is, but it is related to the sphere actually. I think. Let's see, how could you do this? It shouldn't be that difficult.
No, I meant, I mean, the two torus ended up being 0 as a generator, as an element in SK2. Is it the case for higher genus? That's really was my question, not just to work it out, or whether it's known.
Oh, right.
Or is it because of the genus?
It is because of the. No, it's actually not that related to the genus. It's related to the fact that well, that this fibers over S1. So
that's
so fibers over S1. I could even have given even a more bare bones example, which is just the circle. So if you just have S1 and you chop it up in the 4 pieces and then you rearrange, then you're going to get 2 copies of the circle. So then anything that fibers over the circle is going to give you, you're going to be able to mimic that cutting, and then you're going to be able to see that it's 0. So I kind of like mentioned very, very briefly that was the motivation for this mapping torus situation. So if you had, like, you know, in pictures, all of them are going to look the same. But if you have any mapping torus, you know, something like this. If you have a mapping torus that fibers over S1, now that you do your gluing parts, you could have cut that mapping torus into pieces, rearranged, and now you don't care about how you glued. So now you get back again, like maybe two mapping tori. So it all everything that fibers over S1 ends up being cut and paste trivial because of that. So it's yeah.
Nice result. Yeah, good. Excellent. Any other questions for Carmen? Okay, if not, let's thank her again. Thank you very much, Carmen, for the very nice talk.
Thank you.